wanted to remind you of some rules of inference that we talked about, and perhaps even verify some of the things that I've been claiming. Okay? So the first rule of inference I talked about, and again, I think it's worth your while to memorize the Latin phraseology that, that these argumentative styles have attached to them. Modus Ponens is the most famous one. Again, you know P implies Q, you know P, therefore what do you know? So you know that every time okay, so P implies Q is true, right? Therefore, if you have P, what follows? Q, okay? You guys do that sort of thing all the time. I'm telling you, this is just intuitive. It's weird that we all agree on this, right? I mean, it's something that's kind of imprinted on our image by God, right? It's not something that you can really explain. I mean, in the end, it's like, okay, why do these rules of inference have any sort of authority at all? Yeah? And there really isn't an explanation for that other than just, look, this has been imprinted on our image. It emanates from God's person. He's the one who commands us right away. He gives us logical commands right away in the book of Genesis, and he tells us over and over again in Scripture to reason, even reason with him at times. That's in the book of Isaiah. He's commanded us to do so, and therefore he's equipped us to do so. So again, if we know P implies Q, that's true, and we know P, then we can conclude Q is a valid form of logical inference. And the way that you verify that is you write down the symbolic logic rendering of it, and what had better be true is that you have a tautology, yes? And it is, okay? A tautology is like no matter what truth combinations of P and Q you have, this kind of formal logical rendering of this is always true, yes? Okay? Modus Tollens, which is really just modus ponens in disguise. Do you know what I'm saying? Because after all, we know that P implies Q is equivalent to what? What is P implies Q equivalent to? Yeah, so like, you know, you have P implies Q, you know that that's true, but that's equivalent to not Q implies not P, all right? So if you have that, and you have not Q, well, therefore, not P. Now you call that modus tollens, but really do you see that it's just modus ponens again? Do you see that? Because after all, I could call not Q, I could call that capital P, okay? And then I could say this implies, I could call this guy capital Q. Do you know what I'm saying? And then I could actually just call this guy, you know, capital P, and then what would I be concluding right here? Capital Q. Do you see what I'm saying? So it's really just modus ponens in disguise. Yeah? Interesting. Okay. Let me move this because move it up here. Okay. All right. So there's modus tollens. Right. So you can conclude not P. Hypothetical syllogism. This is the one, remember we talked about, I said, okay, you know, P implies Q and Q implies R. At first I said, you know, what do you think about that? And you said, well, that sounds like it might be equivalent to P implies R. Then we thought about it and we're like, oh, what we're actually thinking in our mind is that there's a form of inference happening here. I'm allowed to conclude something based on those two things. So if I know that P implies Q is true, and I know that Q implies R is true, what can I conclude? P implies R, yeah? Overall, that like forms a little chain, yes? P implies R. I'm allowed to conclude that, okay? And that's what this thing is right here, okay? Now, that makes sense to us, hopefully. as a valid form of logical inference called hypothetical syllogism. Sometimes people call this transitive, like it's the transitive property. It's sort of like it's a transitive thing that's happening. P implies Q implies R, so therefore P implies R, yeah? Okay. Moving on. Disjunctive syllogism. Okay, disjunctive syllogism. Okay, and this is like, to me, I always like to think about the left-hand, right-hand thing. Okay, I am either left-handed or I am right-handed. I am not left-handed. Therefore what? Therefore I am right-handed. So you know that P or Q is true. You know that not P is true. Therefore P is false. Does that make sense? Not P being true means P is false. Therefore, for the or to still be true, what would have to be true? Q. Yeah? That's what's going on. But it makes more sense if you just say, I'm either left-handed or right-handed. I am not left-handed. Therefore, I'm right-handed. You kind of just see it clearly flowing when you think about it that way. You guys know, or we've at least talked about the fact that P implies Q is equivalent to not P or Q. We've talked about that, right? And that the negation of P implies Q is equivalent to what? Like I would have to negate that or using De Morgan's law. And so it would be what? Pn not Q, exactly right, okay? So this guy right here, this is a sort of a weird rendering of this, but P implies Q is equivalent to not P or Q, right? The negation of the if part or the conclusion, yes? Okay? And let's just kind of think about that intuitively. It's not quite as intuitive, but I like to use the example of, well, let's just do it with the get an A on the final situation. If I say, if you get an A on the final, then you'll get an A in the class. That's my solemn oath to you. Another way I could say that, and it would actually be equivalent, even though it might sound weird, I might say, either you didn't get an A on the final, or what? Either you didn't get an A on the final, or you got an A in the class. Those are the two things, right? I'm telling you those are equivalent if you go and kind of chew on that for a while. Those two things are equivalent to one another. So let me ask you a question. What about not P? What about not P implies Q? What's that equivalent to? Think about it for a second. If I just think about that or statement right there. Not P implies Q is equivalent to P or Q. Does that make sense? So if I go over here, P or Q is equivalent to not P implies Q. So what is disjunctive syllogism really? Yet again, modus ponens. Do you see it? Thing implies other thing. Thing, therefore other thing. Yes? It's modus ponens yet again. Disjunctive syllogism is simply an example of disjunctive syllogism. Yet again. Okay? Or disjunctive syllogism is an example of modus ponens yet again. Okay? So that's interesting, I think. Yeah, any questions so far? Okay. There's one that I want to talk about. Like some of these are just dumb, but you tend to do them sometimes. If you know that P is true, then of course P or Q is true. Does that make sense? I mean, that's just stupid, right? If P is true, then of course P or Q is true. Yes? So that's called addition. I don't even care about you necessarily remembering this. What I more care about is you knowing these four things, and there's going to be one additional one I would like you to know. Addition is just sort of clear. Simplification, if you know that P and Q is true, then of course what? P is true, and incidentally so is Q. Let's just be honest, okay? Right? If you know that P and Q is true, then of course both P is true and Q is true, correct? Okay. And this is sort of another stupid one. It's conjunction, but like if you know P and you know Q, then what do you know? P and Q. Yeah? That's what's implied. And resolution is the one I want you to know. Resolution. Yeah. So what about resolution? Well, so it's not as intuitive, right? So not P or R is one of the things you know, and then you know P or Q. And what's the conclusion? Q or R. All right. The key here is you have the same proposition and its negation participating in both of the ors. And so that allows you to be able to kind of cancel those ones out. Computer scientists use this one all the time to sort of reduce the complexity of the situation by appealing to resolution. Okay, they'll kind of say, okay, look, I see this thing and its negation somewhere, and it's in this disjunction, this or statement. I can actually get rid of that and reduce the amount of complication. Okay. Now it turns out that this is actually harder to understand why it's true, but there is a way to turn this into hypothetical syllogism. Okay. So what I want you to do right now, so remember hypothetical syllogism is the P implies Q, Q implies R, therefore what? P implies R. So what I want you to do with people right next to you is try to turn these things, turn these lines in the resolution paradigm into implications so that you can see why it is just hypothetical syllogism in disguise. That makes sense? So try to turn these things into implications over the next few minutes so that you can see that it's really just hypothetical syllogism. So work on that for a couple minutes. All right, can you guys let me know what you came up with? Someone. Yeah, Ivan.
I started with turning them all into implications, right? So for the first one, you get P implies R.
Okay, so this is P implies R. Yes, that's true.
And then for the second one, you get not P implies Q. And then the third one, you get not Q implies R. And then I realized, well, that doesn't help much. So I flipped the P or Q into Q or P.
Sure. Okay, so not Q implies P is probably the way to go. Yeah.
And then you can see, well, not Q implies P. P implies R, therefore not Q implies R.
So you have a choice, you have choices here in terms of what plays the role of the if part. Does that make sense? Yeah? So what Ivan is saying is, it's better to say not Q implies what? P? And then you can kind of see, hey, the P is like in both places. Does that make sense? And therefore, by hypothetical syllogism, or the transitive rule or of implication, if you want, right? You should be able to conclude not Q implies R. Yes? And is that equivalent to Q or R? Yeah, it is. This is equivalent to not Q implies R. Indeed. So hypothetical syllogism. So look, we reduced, so there's five big sort of argumentative paradigms that I'm wanting you to kind of know the Latin phraseology for. Modus Ponens, Modus Tollens, disjunctive syllogism, hypothetical syllogism, and resolution. But it turns out that really there's only two. What are really the only two forms? Yeah. Right, modus ponens and hypothetical syllogism is really it. Now you could go to Chuck's and try to think about whether those two are really the same or not. But we've been able to reduce everything to one of two argumentative forms after replacing things with logical equivalences, either modus ponens or hypothetical syllogism. Those two are the most important for sure. But resolution is a powerful, argumentative form that is used very widely. Okay? Questions on that? I think that's cool. But I think all this stuff's pretty cool. So you may disagree. So how about this? So there's a valid arguments. Okay. Come up. So this might look sort of fairly complicated, but I want you to use all of the argumentative things that we know. So for instance, right, modus ponens, modus tollens, disjunctive syllogism, hypothetical syllogism, and resolution. This looks like a complicated collection of statements, but I would put them in symbolic form and try to come up with a way that we could conclude we will be home by sunset from all of these English phrases that are sitting right here. Yes? Okay, so try to come up with that. I'm telling you what the conclusion is, right? This is like what you're driving toward. Now, you might have to make several other conclusions before you make that one. Does that make sense? So there might be two things that imply something, et cetera, et cetera. So think about this for like 5 minutes together or something like that. And by the way, convert everything to like letters and symbols, right? So convert everything to letters and symbols and then see what you can conclude from these things. So let's take some time to do that as well. Okay, go for it. All right, Colby, was the first sentence relevant in any way? You don't think so? Well, maybe, okay, it's an and statement. Remember, anytime you have an and statement that you know to be true, you can always conclude either one of the things. Does that make sense? That's called simplification. That was one of the ones, and I think it, at least the way I was thinking about it, I think it was helpful. But okay, so let's let me write some stuff down here. So it is sunny this afternoon. Okay, it is sunny this afternoon. Oh, it is not sunny this afternoon. Okay, yeah, all right. So let me see, this statement, it is not sunny this afternoon and it is colder than yesterday. So not sunny, and notice I was trying to mess you up by having lots of things with S's and multiple things with C's also, right? So you just have to be careful with that. Not sunny and what? Colder and cold or something, okay? Okay, in this one, I was curious to see what you guys thought, only if, right? So what is that? Only if, okay? What does that mean logically? We will go swimming only if it is sunny. Yes. It's not, well, it's part of it. That would have been if it was if and only if. It's only one, it's one direction, but the question is, which direction is it? Okay, so which is it? Does swimming imply sunny? Or does, oh, okay, or sunny imply swimming? I think it's swimming, because I would have said, we will go swimming if it is sunny. That would have means if it's sunny, then we would have gone swimming. But this is like, we will go swimming only if it is sunny, yeah? So that means swimming, us going swimming, implies that what was the case? It's sunny, okay? So swimming, let's use W for that. Swimming implies what? Implies sunny, okay? Make sense? You just have to think about the two possibilities. What Monique said was if and only if. Like if I would have said, we'll go swimming if it is sunny, that means that being sunny implies that we will go swimming. Does that make sense? But what we're saying is we don't necessarily have to go swimming, but if we do go swimming, that implies what? It is sunny. Yeah? Okay, if we do not go swimming, then we will take a canoe trip. Okay, so how do I capture that? Not W. You guys see that? Not W implies, I don't know, T for trip. Does that make sense? Okay. And if we take a canoe trip, okay, so I don't know, let's see here. This last thing. If we take a canoe trip, so T, then we will be home by sunset. Uh-oh, I'm running out of letters. Oh, home. Yeah, that's a good one. T implies H. Okay? All right, so help me out here. I have these 4 things that are true. Yes, Ivan.
So you start with the first two. You can say, well, start with the first one and say, well, not S and C. C isn't used in the rest of it, so you can use simplification. Just say
Yeah.
S.
Not, or therefore, okay, so therefore not S, right? Because not S and C is true, therefore not S, this is just simplification. Okay? Okay, therefore, okay, now what?
And then from there, you say, well, if you have W implies S,
Uh-huh.
we don't have S, therefore we can't have W.
Okay, right, and so what you're thinking of is which, right, so, I mean, you could think about it one of 2 ways. You can either think of this as being not S implies not W, or you could just invoke Modus Tollens, yeah? So therefore, not W, this is Modus Tollens, yeah?
And then we have, we can kind of forget that for just a second. We can change the last 2 to not W implies H with hypothetical syllogism.
Yes, not W implies H, that's hypothetical syllogism. Yes?
We have not W.
Uh-huh. Therefore, H. That is, okay, what did I just invoke? I just invoked modus ponens on the last, on these guys right here. Does that make sense? Yeah, so this is modus ponens. Okay? Done. I don't know if you could do it in fewer steps than that, but did other people have similar things? And that's sort of interesting, right? Weird how that worked, right? You just went, and then it kind of worked out, yeah? Now, I mean, I think that probably would have been, you know, maybe hard to come up with, like if someone just uttered all those phrases without you actually sitting down and looking at it and trying to sort out all of the pieces, right? But this is a valid conclusion based on those things, for sure. Okay? Cool. Any questions on that? I think those sorts of things are pretty fun. But I'm also a strange guy. Okay? All right, moving on. So there's a couple of things that feel sort of obvious, but that we need to know. Okay? There's something called universal instantiation, which basically says you have some kind of universal statement about everything, and you want to specialize to one particular person or one particular element within your universe. Okay? So like I might say, everyone in this class has taken algebra. And then to universally instantiate would be me saying, Hannah has taken algebra. Does that make sense? That's all you're doing. Is that a valid form of argument? Yes, it definitely is. In fact, like, you know that for all x, p of x, that this is really just equivalent to a giant and. Does that make sense? This is a giant and you're taking the and over all possible x of P of x, yes? And therefore, universal instantiation really is just which valid form of argument when you think about it. We just used it on the last thing. Right, the sentence that Colby at first was kind of like, I don't know if we really need that one. It was this and that, right? And we just ignored the canoe part or whatever it was, yes, or the cold part, and we said, well, this one's important, the not sunny part. You see that that's kind of what we're doing here. We have P of x, like this and this and this and this, right? It's just a giant and statement. All we're doing is specializing to one of them. This is just a form of simplification. Okay? The domain of x is all dogs. Fido is a dog. Okay? All dogs are cuddly. Therefore, what? Fido is cuddly. Make sense? How cute. Yeah? All right. Any questions on that? Hopefully that makes sense. Okay. Universal generalization. So universal instantiation, you go from big to specific. Does that make sense? In universal generalization, you go from like an arbitrary singular thing to everything, okay? So you want to think of, okay, P of C is true for any C I pick. Therefore, the universal statement for all x, P of x is true, yeah? It's kind of strange. So you're kind of going from specific, but not necessarily, because the C could be an arbitrary C, okay? I could say any individual student in this class has taken algebra. Any individual student in this class has taken algebra. Therefore, what? All students in this class have taken algebra, yes? So here you're kind of going to vaguely specific to universal, okay? But it's actually really important that this thing be arbitrary, right? Because you need to know that they're all true, yeah? Okay. Domain of x is all dogs. We know that given any random dog, the dog is cuddly. Therefore, what? For all dogs, the dog is cuddly is true, right? I mean, you could just say all dogs are cuddly, I guess. Makes sense? So universal instantiation, universal generalization, yes. Yeah, basically it is. But in mathematics, a lot of times because when you're in the proof, it's not really possible to treat every possible, like for instance, I might be making a claim about all possible integers. Does that make sense? And it's not possible for me to like say, okay, 1. Is it true for 1? Yes. 2. Is it true for 2? Yes. 3. Wait a minute. I'm never going to finish this until I actually die, right? I mean, and then I'll pass it on to my children, and then they'll never finish, and they'll die, and then on it goes. So in mathematics, a lot of times what you do instead is you say, okay, I'm going to pick a generic integer, and I'm going to see what I can say about that. Does that make sense? And because that integer was arbitrary, that actually extends to the for all statement. So it's useful to be able to talk about a specific arbitrary one for the purposes of proving things. Yeah? All right? Good question. We have universal instantiation, universal generalization. So guess what else we're going to have? Universal. What were the two quantifiers? The for all and there exists, yeah? So we're probably going to have existential instantiation and existential generalization, yeah? Okay? So existential generalization, that sounds like some kind of philosophical crisis or something, right? Existential generalization. Look, if P of C is true for some C, then the existential statement is true, yeah? So if I say there is someone in this, okay, so for instance, I say Austin has taken calculus. Then what could I conclude from that? What is this saying? Yeah, that's right. There is a student in this class that's taking calculus. Does that make sense? That's what existential generalization is. I'm kind of staring at one individual, and I know that I have the truth of the statement for that one, and therefore I'm able to generalize that to the existential statement for the whole domain. Yeah? Okay. Michelle got an A in the class. Therefore, someone got an A in the class. Okay? Yeah, so a lot of times, you know, people will say, did anyone get an A on this test? And I will say, yes. Right? Or did anyone get 100% on this test? And I will say, yes. But in my mind, I'm thinking, that person got 100%. Does that make sense? So I'm making sort of a general statement, but in my mind, it's more specific than that. Existential instantiation kind of goes in the opposite direction. Okay, there is someone who got an A in the class. Okay, let's call him or her C, right? Whoever that person is. Maybe it's, you know, Bob or something, yeah? Bob got an A, yeah? You just know that there is a specific person that got an A, and it's okay to talk about that one person, yeah? Okay. So universal and existential instantiation and generalization, yes? So these are things that oftentimes are utilized in the context of logic and proof. Yeah? Make sense? A student in this class did not pass the first quiz. Everyone in this class passed the first exam. Show how the rules of inference for quantified statements lead to the conclusion that someone in this class who passed the first exam did not pass the first quiz. Help me out here. A student in this class did not pass the first quiz. Everyone in the class passed the first exam. How do I conclude from that that someone in this class who passed the first exam did not pass the first quiz?
Use universal instantiation on the second one. Say, well, if everyone in this class passed the first exam, then there exists a student that passed the first.
Yeah.
No matter what student it is. Is that the correct thing to use there?
Well, okay, so a student in this class did not pass the first quiz. So you can actually refer to that student, right? Because, you know, so let's call it Bob. Let's say that it's Bob. Then what do you know about Bob? Bob passed the first exam, right? So Bob, right, Bob did not pass the first quiz, and Bob passed the first exam. Yeah? So we have a specific example of that just by thinking about these things in the context of, you know, in the first case, a student in this class did not pass the first exam. That's, you know, that's an existential statement, and I'm going to the specific instance of Bob, existential instantiation. Yes? The second case, everyone in this class, that's universal, and I'm getting specific. I'm talking about Bob, the same guy from the first sentence, yes? And because Bob both did not pass the first quiz, but passed the first exam, we have found a case of someone who passed the first exam, but did not pass the first quiz. Yeah? Make sense? And therefore, we can generalize to the full existential statement, yes? Like just saying someone is general again, right? So we've gone from specific, namely Bob, to general. So we've done existential what? Generalization in the last case. Does that make sense? So what we did in this first case was what? This was existential instantiation. What did we do in the second case? This was universal instantiation. And then what did we do to get this last statement right here? Existential generalization. Yes? Existential generalization. That's exactly right. We went to the down to the instance of Bob in both cases, and that allowed us to do the existential generalization of that last statement. Okay? Next time is a presentation. Next week, we'll start doing some basic proofs. We'll start using some of this stuff to write down some basic proofs, although it's going to be nothing like what Roper does, you guys.